But all of them are electrophilic addition to double bonds, right? Now we are using a double bonds as a starting point. Then we're going to add a molecule or the groups of atoms to it. It's all because the pi electrons double bonds is a mildly electrophilic. You can imagine that the pi electrons are sitting outside the molecule. It's a little bit away from the nuclei. So they have less control, they're less bound close to get to the nuclei. So they are kind of more accessible for making nucleophilic attack. So that's the reason the pi electrons are becomes functional groups. But that's the nucleophile. So what it's going to be reacting with, the opposite component, the other side is going to be the electron deficient species, which we call the electrophile, right? There are a variety of electrophile, but we talked about the first reaction is the HCl, HBr, because the proton, H plus, is a superb electrophile. It doesn't have any electrons at all, so it's a really good electrophile. So proton is going to be attacked, get by one of these covalent double bonds. That makes one of the other covalents a cation. And this process has a very important things. When you're going to give the cation to either of the covalents making a double bond, probably the more substituted one better get the cation because the more substituted cations are more stable. But this is making the most stable reactive intermediate. Right? That is a key for understanding the regiochemistry. And of course, after carbocation is produced, the nucleophile, which is the bromide, capture the carbocation, and you're going to get that HBr added to double bonds. So that's a regular Markov-Nikov fashion of the adding HBr, right? This is what we studied. And after that, we talked about doing in other order. In order to add things in different orders, we have to do it in different conditions. This is a radical initiated condition. We're still going to add an HBr, but we're going to change the order of the things added. We're adding the proton first to make the most stable carbocation and the most substituted positions. But when you're doing the radical conditions, of course, that radical conditions are produced the bromine radical, and that is going to be the electrophile, not the proton H plus. That is going to be added to the, that is going to be attacked by the pi electrons. Single electron movement here, single electron movement there. So you're going to make a bond between the carbon and bromine. And then again, the most substituted carbon is going to be the radical. So regardless what gets added first, the most substituted carbon is going to be the reactive intermediates. Formal cases, carbocation. Later cases, it's going to be the radical. The radical is going to be capturing the hydrogen from HBr in the second propagation steps, and that will make a hydrogen added on the more substituted positions, and then the bromine goes to less substituted position, which is a different arrangement of the Markov-Nikov. So we call that anti-Markov-Nikov products. So it's even though adding simple HBr, depending on how you do, you're going to get a different outcome. So that's one thing that we start with. After that, what we did, we adding halogen. But there's a different way to adding a halogen to the double bonds. The pi electrons is going to make an attack to the halogens and then break the halogen bond. In this case, bromine bond. So the bromide is going to be released. But this bromine is going to be connected to two carbon as a bridge ion. We call it brominium ion. Bromines are going to be positively charged because bromines are using one of these electron pairs to make a bond with two carbons. So bromine is electron deficient. That's what's brominium ion. And when the bromine is electron deficient, it's not just going to be handling all the pressure by itself. It's going to be asking help from the carbon bound two. And then, so because of that, these two carbon bound to bromine is going to give some of their electrons to it, so they can handle the help. Which carbons afford to give more electrons? Probably the more substituted side, because the help can come from its own substituents too. But this is going to be very key to understanding the reaction like this. You're going to keep seeing things like this, the bridge ion or the cyclic intermediates differently substituted and the more substituted carbon is going to be losing more electrons to stabilize that. This is a theme keep appearing again, the reaction we will discuss later. So anyway, so this is what's going to happen. And the bromine is going to pull the density from both carbons, but the more substituted carbon will lose more. So when there's a nucleophile, they're going to see these carbons are much easy to attack because it's going to be more electron deficient. So the left out bromide is going to make an attack to this carbon and opposite side. Again, the stereochemistry goes in for this case from the opposite side. Because the brominium ions are on top of the top screen, so the bromide has to attack with the bottom of the screen to make the this process goes easier, backside attack. That makes this opens, then you're gonna get the bromine added. But you can see that those two bromines gonna be end up being in trans relationship because it's an anti-attack. That's a bromine added in non-nucleophilic solvent. Non-nucleophilic solvent means that the solvent doesn't have anything like oxygen or nitrogen role there. I mean, typically like the chloroform, carbon tetrachloride, the dichloromethane, those type of things that will be used a lot because they don't have oxygen or nitrogen, which can act as a nucleophile. But if you do the reaction, same bromine added in the methanol, water, those type of nucleophilic solvents, what could happen is, first step is you get the same brominium ion. When you make the brominium ion, we expect a more substituted carbon who's more density. This is going to be the most electron deficient carbon between those two. Nucleophile is going to make an attack the same way we did before with the bromide. But in this case, we got other nucleophile in the solution, which is a solvent. Solvent molecule will be less reactive than the bromide here, but it outnumbers it. Solvent molecule means that there's so many of them surrounding it. The backside has so many of them. So this bromide doesn't have to travel from the top side to the bottom side and make an attack. I mean, it's not like that at all in reality. But however, what I'm saying is solvent solvation means it's already surrounding it. So this water molecule or the methanol in this case, then it's already there. And then oxygens are typically not neutral alcohol. Waters are not very nucleophilic. We discussed that before, but however, these things are basically carbocation. It's not exactly carbocation, but it's electron deficient species. Some of the carbocation, like carbon, like here. So these things can make an attack. Same thing for the backside. So you get water or the alcohol substituted on the more substituted side, right? And then the last substituted carbon get the bromine or chlorine, depending on what halogenation ion you get. And that is the haloform reactions. I mean, of course, if it's a water, that's going to be OH, but it can be done with a variety of different solvents. If you're using an alcohol, you get an alkoxy groups there sitting on their positions. So this is still the Markov Nikov products because of the nucleophile. You're going to track where the nucleophile is. If the nucleophile is on the more substituted side, you can easily say that that's a Markov Nikov product. That's kind of a picture. And so this is what we discussed in the last class.